Hi, today we are learning about momentum. We'll mostly stick to one-dimensional momentum today. So momentum is the product of mass and velocity of an object. As such, it is a vector quantity because we have velocity going into it, which also is a vector. So momentum has direction. Our formula for momentum is just mass times velocity. Our units for it are kilogram meters per second or Newton seconds. An example we have is a 1,200 kilogram car is traveling at 25 meters per second to the east, and we want to know what the momentum is. So as usual, write out the information we have. So we've got mass is 1,200 kilograms. Our velocity is positive 25 meters per second because we're going to the east, so that's a positive direction, and we're looking for momentum. So we know our momentum is mass times velocity. In this case, we don't have to rearrange our equation at all. We can just substitute directly into it. And then calculate the appropriate amount of significant figures, and we have 3.0 times 10 to the 4 kilogram meters per second. With momentum, we also have something known as impulse. So impulse is a change in momentum of an object, and as it's a change in momentum and momentum has direction, impulse also has direction and therefore is a vector quantity. Now our units are kilogram meters per second or Newton seconds, and we have a few different equations for it. So impulse can be equal to our change in momentum. Now that can be rewritten as mass times change in velocity, because usually if we have a change in momentum, our mass is staying the same but our velocity is changing. The third formula that we'll sometimes use is it's our sum of forces times time. So it's a force applied for a specific amount of time. So for example, a net force of 35 newtons acts on an object for 1.5 seconds. Calculate the impulse. So we have a net force of 35 newtons. We're given a time of 1.5 seconds. We're calculating our essentially change in momentum, which is our impulse. So we know our impulse is our force times time. In this case, we don't have to rearrange, just substitute in and round to appropriate amount of significant figures. So we have 53 Newton seconds. Now, second part to this question, if object has a mass of 20 kilograms, what is the change in velocity that it experiences? Now we know impulse is equal to mass times change in velocity. So if we rearrange this by dividing both sides by our mass, we get our impulse divided by mass as our change in velocity. Substitute our values in, and we get a change in velocity of 2.6 meters per second. Next example, we have a 12 kilogram object with a velocity of 25 meters per second to itself, has a 50 Newton net force to the north, act on it for 2.5 seconds. We want to know what the object's final velocity is. So we'll start by writing out what information we have. So we know our mass is 12 kilograms. We're starting out to the south, going to the south, so that would mean our initial velocity would be negative. So we've got initial velocity of negative 25 meters per second. We have a sum of forces of 50 newtons and a time of 2.5 seconds, and we're solving for final velocity. So we're going to utilize a couple equations. So we've got this one, that is essentially our impulse or change in momentum, is our sum of forces times time. And this one where our impulse or change in momentum is mass times change in velocity. Now because each of these equations equals the same thing, the equations therefore equal each other. So we have mass times change in velocity is equal to sum of forces times time. Rearranging this to get our change in velocity on its own, we divide both sides by mass, so we've got our change in velocity is equal to sum of forces times time divided by our mass. Now our change in velocity we know is our final velocity minus our initial velocity, so we can move the initial velocity to the other side by adding it to the other side of our equation. At this point, we have rearranged to get what we're solving for on its own, so I would substitute our values in. and then calculate and put to appropriate amount of significant figures. So we get a final velocity of negative 15 meters per second. Alternatively, because it's negative, we know it's going to south, so we could have said 15 meters per second to the south. So now we're going to start looking at how momentum pertains to collisions in 1D. So collisions are classified into two main groups. So one is elastic, in which both momentum and energy are conserved, and inelastic, in which only momentum is conserved. Now we treat our collisions as if they are isolated systems, so we don't treat them as though they're having external forces acting on them. And to help solve collisions, what we utilize is the law of conservation of momentum. In an isolated system, the total momentum before a collision will be the same as the total momentum after a collision. So we can write this equation-wise as our initial momentum equals our final momentum. Now, today we're looking at linear collisions because we're just looking in one dimension. Next set of notes, we'll look at ones in two dimensions. Now there's three main types of collisions. There's collisions in which objects collide but remain separate. There are collisions in which objects are stuck together and move off together in the end. And collisions in which one object essentially splits apart. So we'll do an example of each type of these collisions. So first example, we have a 0.020 kilogram marble rolling east at 6 meters per second, which collides with a stationary marble that has a mass of 0.025 kilograms. If after the collision, the 0.02 kilogram marble slows to 1 meter per second, we want to know what the velocity of other marble is after the collision. So what I tend to do for solving these is split the equation into before and after collision. And I often draw out what's going on as well. So before the collision, we have one marble that is traveling at 6 meters per second, colliding with one that is stationary. After the collision, we know that the one that was originally traveling at 6 meters per second has slowed to 1 meter per second, but we don't know the velocity of the second marble. So we'll look at calculations for before the collision. So before the collision, the total momentum would be the momentum of marble A plus the momentum of marble B initially. So we can substitute in our momentum equations for each of those. So we have our initial momentum is mass of A times velocity of A plus mass of B times velocity of B. And those are all with our initial values. So we'll substitute our values in. And of course, the second term is going to essentially cancel out because anything times 0 is 0. And we get an initial momentum of 0.12 kilogram meters per second for momentum. Now, because of the law of conservation of momentum, we also know that that is the value of our final momentum. Now we'll look at calculations for what's going on afterwards. So afterwards, we have two objects moving separately, so we can say our total momentum is equal to momentum of A plus momentum of B. We'll substitute in formulas for momentum of A and momentum of B after we do some rearranging. So first we rearrange by subtracting momentum of A to the other side so we can get momentum of B on its own, seeing we're trying to solve for an attribute of B. So we'll substitute in our mass times velocities now. And then we want velocity of B on its own, so we divide both sides by the mass of B. At this point, we have what we're solving for on its own, so substitute our values in. And we get 4 meters per second for our velocity of B. So next example is we have a 6,000 kilogram rail car traveling east at 6 meters per second, collides with a 4,000 kilogram rail car, which we're not given a speed, so we assume it's stationary. the cars stick together, and we want to know what their velocity is after the collision. So once again, I'd split it into before and after and have drawings of what's going on. So before, we have rail car A at 6,000 kilograms traveling at 6 meters per second to the east, while rail car B at 4,000 kilograms is stationary. Afterwards, the cars have linked together, so they're traveling together. So we'd have a combined mass that's the addition of those two masses, and they're traveling at an unknown velocity. So writing out equations for our initial components, so our initial momentum is equal to the initial momentum of A plus the initial momentum of B. We can substitute in our momentum equations for each of those, and then substitute our values in. Calculating our initial momentum, we get 36,000 kilogram meters per second, and because of conservation of momentum, that's also our final momentum. Afterwards, our momentum's just equal to this one object that's moving off as one solid piece. So momentum afterwards is just equal to momentum of A and B combined. We can substitute in mass times velocity for that. And then we want velocity on its own, so we'll divide both sides by MAB. Fill in our values, so we have our final momentum, which we already calculated. And then the mass of AB is our 6,000 kilograms plus our 4,000 kilograms. And we get an after collision velocity of 3.6 meters per second. Next example, we have a 3 kilogram rifle fires a 0.005 kilogram bullet at a speed of 300 meters per second. And we want to know at what speed does the rifle recoil, so how fast does it kick back. So once again, I'd start by splitting up into before and after. So before, I have the rifle that has the bullet inside it. They're both stationary. And afterwards, the bullet's moving forward at 300 meters per second while the rifle recoils at an unknown velocity. So if we look at our before momentum, we can see that nothing is moving, and because momentum requires velocity and our velocity is 0, mass times 0 is 0, so our initial momentum is 0, which means our final momentum also has to equal 0. After the gun is fired, we have two separate things moving, so we can say our momentum is equal to momentum of the rifle plus the momentum of the bullet. I would move the momentum of the bullet to the other side of our equation. And then we can get rid of our final momentum because we know it's equal to 0. So 0 minus momentum of bullet would just be negative momentum of the bullet. We can then substitute in our mass times velocity for each of those, and then divide both sides by the mass of the rifle. Substitute our values in, and we get that recoils at negative 0.5 meters per second.